A cosmic whirlpool 25 million light-years away hides 28 bizarre secrets. The Pinwheel Galaxy appears as a perfect spiral in the night sky, but this beautiful facade conceals a chaotic reality of unexplained explosions, missing black holes, and structures that defy our understanding of physics. By the end of this journey, you will see this familiar galaxy in a completely new and startling light. Why does its core appear to be missing a supermassive black hole? And what is the true nature of a light source so bright it should not exist? What cosmic mystery would you most want to solve for yourself? This perfect spiral was torn by an impossible star. In 2011, astronomers witnessed a stellar explosion inside the Pinwheel Galaxy, an event cataloged as SN 2011 FE. It was a Type 1, a supernova, the kind used as a standard candle to measure the vast expanses of the universe. But this one was different. Its brilliant flash was far too powerful. According to our fundamental rules of physics, a white dwarf star, the dense corpse of a sun-like star, should explode the moment it gains enough mass to reach a critical threshold known as the Chandrasekhar limit. It is a cosmic boundary, a point of no return. Yet the light from SN 2011 FE told a different story. The data suggested this white dwarf did not explode at the limit. It somehow bulged with mass, pushing far beyond what should have been possible, becoming a super Chandrasekhar object before it shattered. It was like watching a glass fill with water, not just to the brim, but beyond, defying gravity itself for a fleeting moment before it finally overflowed. How could a star break a law of physics we thought was absolute? This single event sent ripples through the world of cosmology. If the standard candles we use to map the cosmos are not so standard after all, what does that mean for our measurements of dark energy, the mysterious force accelerating the universe's expansion? Our entire cosmic distance ladder might be resting on a foundation that is far less stable than we believed. That single supernova was not the only rule breaker in this spiral galaxy. The pinwheel presents an even deeper enigma at its very heart, a profound absence where there should be a titan. Almost every large galaxy we know, including our own Milky Way, anchors itself around a supermassive black hole, a gravitational monster millions or even billions of times heavier than our sun. Yet when astronomers peer into the core of the Pinwheel Galaxy, they find a perplexing void. The telltale signs are missing. There is no intense radio beacon, no frantic whirl of stars orbiting an unseen point of immense gravity. It is as if the throne at the center of this cosmic kingdom is empty. So where did the monarch go? One compelling theory suggests the black hole is not gone, but merely sleeping. It could be an unusually quiet, starving black hole, one that has consumed all the nearby gas and dust, leaving it in a state of deep hibernation without a meal to power the brilliant, energetic displays we typically associate with these cosmic beasts. It is there but silent and dark. A more dramatic possibility involves a violent past. Galaxies often collide and merge, and when their central black holes spiral toward each other, the resulting gravitational dance can fling one of them clear out of the galaxy entirely. Imagine two titans locked in a cosmic wrestling match, and the loser is hurled into the intergalactic void, a king without a kingdom, leaving behind only a quiet and strangely peaceful core. This absence forces us to question a fundamental assumption about how galaxies form and live. Is a supermassive black hole the essential heart of every large galaxy, or can some, like the pinwheel, exist without this dark anchor? The quiet at its center is not peaceful. It is a silence that screams with questions. The silence at the galaxy's core is broken by a beacon of pure power. Elsewhere in the pinwheel's spiral arms, a pinpoint of light shines with an intensity that should be impossible. Astronomers know it as ULX-1, an ultraluminous X-ray source. It is not merely bright, it is one of the most brilliant objects of its kind ever seen, pouring out more X-ray energy than a million suns. This raw power directly challenges one of astronomy's fundamental rules, the Eddington limit. This limit dictates the maximum brightness an object can achieve based on its mass. Think of it like a campfire. A small fire can only get so bright before its own radiation pushes the surrounding air away, starving it of fuel and preventing it from burning any brighter. For a typical stellar mass black hole, the kind formed from a collapsing star, there is a strict brightness ceiling, yet ULX-1 smashes through this ceiling with ease. How can it burn so fiercely without tearing itself apart? One leading theory suggests we are not looking at a standard black hole at all, but a long-sought missing link, an intermediate mass black hole. This would be a cosmic middleweight, far heavier than a single star but not quite a supermassive giant. With more mass, its gravitational grip is stronger, allowing it to pull in and devour matter at a ferocious rate without hitting the same radiation limit. Its greater mass simply allows for a brighter fire. Another, even more intriguing possibility is that we are witnessing a stellar black hole in a state of extreme and messy gluttony. In this super Eddington state, the black hole is consuming material so rapidly that the infalling gas and dust form a thick, dense shroud around it. The radiation struggles to escape this chaotic environment, building up immense pressure until it erupts in powerful, focused-out flows like a pressure cooker releasing steam. In this scenario, the object is not breaking the laws of physics, but rather bending them through a complex and violent feeding frenzy. So the brilliant flare of ULX-1 presents us with two equally fascinating mysteries. Is it a new class of black hole, a hidden middle child in the cosmic family, or is it a familiar object behaving in a radically new way, showing us a limit we thought was absolute is merely a suggestion under the right conditions? This beautiful symmetry is an illusion. Look closer at the pinwheel's majestic spiral arms, and you will see they are not a perfect, balanced pinwheel at all. One side of the galaxy appears more stretched and open, while the other is tighter and more compact. This cosmic lopsidedness provides a live-action view of a gravitational tug-of-war happening on an unimaginable scale. The primary culprit is thought to be one of its own satellite galaxies, a smaller companion known as NGC 5474. This smaller galaxy is not simply orbiting peacefully, it is engaged in a slow, relentless dance with its larger host. As it swings by, its gravity exerts a powerful pull on the pinwheel's outermost stars and gas, stretching one of the spiral arms like cosmic taffy. This process is driven by tidal forces, the same kind of gravitational interaction that causes Earth's ocean tides from the moon's pull, but amplified to a galactic level. Here, these forces are not just moving water, they are reshaping the very structure of a galaxy. We are witnessing galactic evolution in real time, a process that typically unfolds over hundreds of millions of years. This asymmetry is not a flaw, it is a snapshot of a dynamic relationship, a testament to the fact that no galaxy is an island. Each exists within a web of gravitational influence, constantly being molded and reshaped by its neighbors. What other subtle distortions might we find if we look even closer at this seemingly familiar whirlpool of stars? These distorted spiral arms are not just being stretched, they are also bursting with new life. While gravity tugs at the grand structure within the arms themselves, pockets of cosmic gas and dust are collapsing into a stellar firestorm of creation. The Pinwheel Galaxy is a prolific star factory, and its most active production lines are colossal clouds known as H2 regions. These are not just any nebulae, they are stellar nurseries on an epic scale, far larger and more intensely active than any found in our own Milky Way. Take NGC 5461 and NGC 5462 for instance. These are not single stars, but vast glowing clouds of hydrogen gas that have been ionized, their atoms stripped apart by the fierce ultraviolet radiation from thousands of newborn, incredibly massive stars within them. To stand on a hypothetical planet near one of these regions would be to see a sky dominated not by a gentle Milky Way, but by a continuous, blazing light show of young, blue-white suns and glowing gas clouds that dwarf the Orion Nebula in both size and brilliance. These are the places where stars are born, not in quiet solitude, but in frantic, crowded clusters. Why does this matter to us, watching from millions of light years away? These extreme environments are our cosmic laboratories. By studying the frantic pace of star birth within NGC 5461 and NGC 5462, we can understand the specific conditions, the perfect storm of dense gas, shockwaves, and turbulence that gives rise to the most massive stars in the universe. These are the stars that live fast and die young, exploding as supernovae that seed the galaxy with heavy elements and reshape the gas around them, triggering yet more rounds of star formation. The pinwheel's vibrant arms are not just a beautiful feature, they are a key to understanding the violent, creative cycle that builds galaxies and forges the very elements that make planets and life possible. But what happens when this cycle of creation goes into overdrive, producing not just stars, but objects so strange they challenge our very definitions. This brilliant star formation is all held together by an unseen hand. For the Pinwheel Galaxy to maintain its majestic spiral shape, something invisible must be providing an immense amount of extra gravity. The stars and gas we can see simply do not add up to the force required to keep the galaxy from flying apart. The evidence for this hidden mass comes from a fundamental measurement called the rotation curve. As astronomers track the speed of stars and gas clouds orbiting the galaxy's center, they expect to see those on the outer edges, far from the bright central bulge, slowing down significantly. Just as Pluto orbits our sun more slowly than Earth, a star at the galaxy's fringe should be crawling along, but that is not what happens. Instead, stars on the outer rim race around at nearly the same speed as those closer in. It is as if the entire galaxy is embedded within a colossal, invisible sphere of mass, a dark matter halo. This halo does not emit any light or radiation we can detect. It is a ghostly gravitational scaffold, and without it, the Pinwheel Galaxy would unravel. Its spiral arms would not be able to hold their form against the centrifugal force of their own rotation. This dark matter is the TRUE Chinese letter of the galaxy, the hidden framework that dictates its very architecture. But what is the shape of this phantom structure? Current models suggest the halo is not a perfect sphere, but a slightly flattened, diffuse cloud that extends far beyond the galaxy's visible edge. Its gravitational influence is so vast that it governs the motions of the Pinwheel satellite galaxies, holding them in a wide, cosmic embrace. These smaller galaxies are not just passing by, they are trapped in orbit around the invisible halo. Their paths is silent testimony to the dark giant that dominates this region of space. This unseen presence raises a profound question. Is dark matter the ultimate puppet master, quietly orchestrating the formation and fate of every large galaxy in the universe, with the beautiful pinwheel as just one visible manifestation of its invisible power? This phantom halo of dark matter may have helped forge an entirely new galaxy. At the very edge of the pinwheel's visible disk, astronomers have spotted a strange, dense clump of stars and gas. It appears detached, a cosmic island that seems to be drifting on the periphery of the grand spiral. This is not a typical star cluster, nor is it one of the known satellite galaxies. The leading hypothesis is that we are looking at a tidal dwarf galaxy candidate, an object born from violence and chaos. If confirmed, this clump will be a galaxy in its own right, but one with a very different origin story from most. It was not born from a primordial cloud of dark matter in the early universe. Instead, it was likely forged in the gravitational turmoil of a past galactic collision. The theory goes that during a close encounter, perhaps with its satellite companion, vast streams of gas, dust, and stars were ripped right out of the pinwheel's spiral arms by immense tidal forces. This stolen material, rich with the ingredients for new stars, was flung into space, but instead of simply dispersing, it began to collapse under its own gravity, coalescing into this new, tiny galaxy. It is a celestial phoenix, rising from the debris of a galactic interaction. The evidence for this is compelling. The chemical makeup of the stars in this clump is different from that of the old, primordial satellite galaxies. They are metal-rich, meaning they contain a high abundance of elements heavier than hydrogen and helium, which are forged in the hearts of stars and scattered by supernova. This points to a birth from gas that was already enriched by previous generations of stars, gas that was once part of the pinwheel's own spiral arms. However, the classification is not yet certain. The case against it being a true tidal dwarf galaxy hinges on one crucial ingredient: dark matter. Traditional dwarf galaxies are dominated by it, held together by its invisible grip. But a tidal dwarf, formed from the collisional debris of larger galaxies, should be made almost entirely of normal baryonic matter, the stuff we can see. It should be a galaxy of pure starlight and gas, with very little dark matter at its core. Proving this one way or the other is incredibly difficult, as detecting the presence or absence of an invisible substance in such a distant object is at the very limit of our technology. So this mysterious clump presents us with a profound choice. Is it a new type of galaxy, born from the wreckage of a cosmic fender bender, a living testament to the recycling of galactic material? Or is it something else entirely? Its very existence forces us to ask, how many of the small galaxies we see scattered throughout the cosmos were born not from the dawn of time, but from the violent, ongoing dance of their larger neighbors. Scattered throughout the pinwheel's vast expanse are ancient cosmic relics, and some of them shine with a light that defies expectation. These are globular clusters, dense spheres of hundreds of thousands of stars, all bound together by gravity. They are typically old, quiet cities of stars, fossils from the earliest days of a galaxy's formation. But within M101, many of these clusters are not just old, they are astonishingly brilliant and massive, far outshining their counterparts in our own Milky Way. What could create such luminous stellar collectives? Their extraordinary brightness suggests they are packed with a much larger number of stars than normal. One compelling idea links their formation directly to the galaxy's turbulent past. The Pinwheel Galaxy is thought to be the product of a violent merger, a colossal crash between two smaller galaxies in the distant past. During such a cataclysmic event, the normal, gentle process of star formation is thrown into chaos. Vast clouds of gas are violently compressed, not just forming individual stars, but triggering the birth of immense, super-sized star clusters in a single, frantic burst. These brilliant clusters are the lasting legacy of that ancient collision, cosmic monuments built from the shockwaves of a galactic wreck. This suggests a different class of cluster formation altogether. In the relatively calm environment of the Milky Way, globular clusters form slowly and steadily. In the chaotic forge of a galactic merger, they were born in a firestorm, emerging as giants from the very beginning. Their unusual luminosity is a permanent record of the incredible forces that shape their home. What other ancient scars might these brilliant clusters be hiding within their tightly packed stellar cores? Even these brilliant clusters can act as windows to something far more distant. The immense gravity of the Pinwheel Galaxy does more than just hold its own stars together. It subtly bends the very fabric of space around it. This creates a natural cosmic lens, a phenomenon known as gravitational lensing. Imagine space as a stretched rubber sheet, and a massive object like a galaxy creates a deep dip in that sheet. When light from a background object travels toward us, it follows the curve of this dip, its path bending around the foreground galaxy. The result is not a perfect magnifying glass, but a natural telescope that can distort, brighten, and even multiply the image of galaxies that lie billions of light years behind it. The Pinwheel Galaxy, in all its sprawling majesty, becomes a foreground lens, and astronomers have learned to peer through its gravitational warp to see the universe beyond. In a single telescope frame aimed at M101, we get a double cosmic vista. We see the detailed structure of the pinwheel itself, a galaxy 25 million light years away, and superimposed upon it, the faint, smeared or stretched shapes of galaxies from the deep, deep past. These are high redshift galaxies whose light has been traveling for so long that we see them as they were when the universe was young. It is like looking through a window and seeing not just your own backyard, but a landscape on the other side of the world, all at once. By carefully analyzing how the pinwheel's gravity distorts the light from these ancient background objects, astronomers can perform a kind of cosmic weigh-in, measuring the total mass of the pinwheel, including both its visible stars and its vast invisible dark matter halo. Each distorted galaxy is a data point, a silent witness to the total gravitational pull of the foreground spiral. So this beautiful galaxy is not just a subject of study, it is a scientific tool, offering us a glimpse into two different eras of cosmic history with a single observation. What other ancient secrets might be hiding, magnified in the warped light around its spiral arms? This lens of gravity reveals a galaxy that is far larger than it appears. While our telescopes capture the pinwheel's brilliant spiral of stars, they miss a vast invisible ocean of raw materials swirling around it. This is neutral hydrogen gas, the primary fuel for star formation, and in M101, its distribution is anything but orderly. Observations show this cold gas is not a smooth, placid disk. Instead, it is clumpy and fragmented, a choppy sea of cosmic fuel, and it stretches out to distances far beyond the galaxy's visible edge. The bright pinwheel we see is actually embedded within a colossal, faint halo of atomic hydrogen, a ghostly echo of the galaxy's true, much larger form. What could have churned this gas into such a turbulent and extended state? The most likely culprit is the galaxy's dynamic history of gravitational encounters. Each close pass by a satellite galaxy like NGC 5474 sends powerful ripples through this gaseous reservoir. These tidal forces stir the hydrogen, piling it up into dense clouds and filaments in some regions while stretching it into long, faint streams in others. It is like dragging a stick through a placid pond, creating swirls and eddies where there was once calm water. This chaotic distribution is a fossil record of past interactions, a permanent imprint of the gravitational pushes and pulls the galaxy has endured. But this disordered gas is also the key to the galaxy's future. Every one of those dense clumps is a potential stellar nursery, a pocket of fuel waiting for the right trigger, a shockwave from a nearby supernova, or the pressure of a spiral density wave to collapse and ignite into new stars. The extended halo of gas represents an enormous reservoir, a deep well of potential that could fuel star formation for billions of years to come. Yet this bounty is also precarious. If another galactic interaction is violent enough, or if the pinwheel were to fall into a dense galaxy cluster, this loosely bound hydrogen could be violently stripped away, ripped from the galaxy by even stronger tidal forces, or by the intense pressure of plowing through intergalactic gas. The galaxy would be left starved, its future star formation quenched, its spiral arms slowly fading as the last of its fuel is consumed. So this anomalous, clumpy hydrogen is more than just a curiosity. It is a snapshot of a galaxy caught between its past and its future, its form still being shaped by ancient collisions, its destiny written in the distribution of an invisible, swirling sea. This faint, lingering whisper of light carries a message from the dead. In 2004, astronomers studying the Pinwheel Galaxy detected a series of faint, expanding rings of light emanating from the location of a supernova that had been observed more than a century earlier. The star had died in 1909, its brilliant flash long since faded from view, yet here was its ghost still visible. This phenomenon is a light echo, one of the most elegant tools in an astronomer's kit. When that supernova erupted over a century ago, its intense flash of light radiated outward in all directions at, of course, the speed of light. The light that traveled directly toward Earth arrived in 1909, and we saw the explosion. But some of that light traveled on a different path. It raced outward until it slammed into vast, dark clouds of interstellar dust located light years away from the original star. These dust clouds act like cosmic mirrors, reflecting a small fraction of that light back toward us. Because this reflected light had to take a longer, scenic route, it arrives at our telescopes decades, or even centuries, after the main event. We are not seeing the explosion itself a second time, we are seeing its reflection, a delayed broadcast from the past. This gives modern science an incredible opportunity, a chance to perform a postmortem on a stellar cataclysm that human eyes witnessed over 100 years ago. By analyzing the spectrum of this echoed light, astronomers can dissect the chemical composition of the exploded star long after the debris has cooled and dispersed. It is like having a time machine that allows us to re-examine a crime scene with modern forensic techniques long after the initial evidence has gone cold. We can determine what kind of star it was, what elements it forged in its final moments, and confirm the type of explosion it underwent. This particular echo from the Pinwheel Galaxy confirmed that the 1909 event was a Type II supernova, the core collapse explosion of a massive star many times heavier than our Sun. Every new light echo we discover is another chapter in a cosmic history book, allowing us to study the deaths of stars we thought were lost to time. What other ancient stellar explosions are still whispering their secrets to us, their light slowly bouncing its way through the dusty halls of the galaxy? These light echoes are not the only timekeepers in the Pinwheel Galaxy. Scattered among its spiral arms are stars that beat like cosmic metronomes, their rhythmic pulses holding the key to the vast scale of the universe. These are Cepheid variable stars, and M101 possesses one of the most significant populations known. A Cepheid is a star in a late stage of its life, a giant that has become unstable. It rhythmically expands and contracts, growing brighter and dimmer over a regular cycle that can last from days to months. This pulse is not random, it is a fundamental property of the star, directly tied to its true intrinsic brightness. A Cepheid with a long period is inherently more luminous than one with a short period. This period luminosity relationship, discovered over a century ago, is one of the most powerful tools in cosmology. It allows astronomers to measure distances with remarkable precision. By simply observing the pulse rate of a Cepheid, they can determine its true power, and by comparing that to how dim it appears from Earth, they can calculate exactly how far away it is. These stars are the first crucial rung on the cosmic distance ladder, the method we use to measure the universe itself. The Pinwheel Galaxy's rich collection of Cepheids was instrumental in confirming its distance of 25 million light-years, solidifying our place in the cosmic neighborhood. Yet even here among these trusted mile markers, anomalies appear. Some Cepheids in M101 pulsate with periods or brightness levels that deviate slightly from the expected model. They are the cosmic equivalent of a clock that ticks just a little too fast or too slow for its size. What could cause such a reliable standard to waver? One possibility lies in the star's chemical makeup. Stars formed in different parts of a galaxy can have different compositions, with varying amounts of elements heavier than hydrogen and helium, what astronomers call metallicity. A star with higher metallicity has a different internal structure and opacity, which can subtly alter its pulsation mechanics and its ultimate brightness. The Cepheids in the Pinwheel's metal-rich spiral arms might not behave exactly like their counterparts in other, chemically distinct galaxies. Another factor is the star's environment. A Cepheid blazing away inside or near one of those intense H2 regions, like NGC 5462, is surrounded by thick clouds of gas and dust. This interstellar material can absorb and redden the star's light, making it appear dimmer and farther away than it truly is, throwing off the delicate calibration of the distance measurement. These are not flaws in the stars themselves, but complexities in our interpretation. Each anomalous Cepheid forces us to refine our models, to add new layers of understanding to the simple, beautiful relationship between pulse and power. They remind us that the universe is never as simple as our equations, and that even our most trusted guides require careful, constant observation. If the very stars we use to map reality can surprise us, what other assumptions on the grandest scales might need a second look? These stellar pulsations are just one rhythm in a far more violent galactic symphony. Across the Pinwheel's sprawling arms, the combined fury of countless supernovae and the relentless pressure of stellar winds from massive young stars are not just creating chaos locally. They are generating colossal outflows that stretch far beyond the galactic disk. These are galactic winds, vast rivers of hot gas being blown clear out of the galaxy itself. Imagine the frantic energy of a star factory like NGC 5462, but amplified across the entire spiral structure. Each supernova explosion acts like a titanic piston, and the constant stream of particles from massive stars is an unending gale. Together, they heat the surrounding gas to millions of degrees until its pressure becomes so immense that it bursts outward, flowing away from the disk at speeds of hundreds of kilometers per second. We do not see this directly in visible light, but its signature is written in the X-ray glow of superheated gas and in the subtle shifts of radio emissions, telling us of material rushing away into the void. This process is a fundamental form of cosmic regulation. A galaxy can only form stars if it has a reservoir of cool, dense gas. By violently ejecting this raw material back into intergalactic space, the galactic wind effectively starves the galaxy of its own future fuel. It is a self-limiting cycle where the very act of frenzied star creation eventually shuts down the production line. For a galaxy like the Pinwheel, currently in a burst of stellar birth, these winds are a testament to its own incredible power. They are the galaxy's own breath, hot and heavy with the elements forged in its stellar furnaces, and they are slowly sculpting its destiny, one supernova at a time. What becomes of all this ejected matter as it flows into the silent darkness between galaxies? This wind of hot gas does not simply vanish into the void. Some of it flows outward until it falls under the gravitational sway of a smaller neighbor, and one companion in particular seems to be feasting on the Pinwheel's exhaust. The dwarf galaxy NGC 5477 is a tiny, irregular splash of stars nestled close to the grand spiral, and it is currently in the throes of a spectacular starburst. For its small size, it is producing new stars at a ferocious, almost frantic rate. Why would this little galaxy be so brilliantly aflame? The evidence points directly to its giant neighbor. Galaxies orbiting each other are linked by more than just gravity. They are connected by rivers of gas. As the Pinwheel Galaxy blows out its superheated galactic wind, This material, enriched with heavy elements from countless supernovae, can stream across the intergalactic gap and pour into the waiting arms of NGC 5477. This influx of fresh, dense fuel is the perfect trigger for a wave of star formation, like throwing a bucket of gasoline onto a smoldering fire. But there is another, even more powerful mechanism at play. The recent close passage of the dwarf galaxy, swinging by the immense pinwheel, would have sent colossal tidal forces rippling through its structure. Just as the moon's gravity stretches Earth's oceans, the pinwheel's gravity would have compressed the gas clouds within little NGC 5477, squeezing them violently and triggering their collapse into new stars. It is a one-two punch of galactic interaction. First, the tidal squeeze provides the initial compression, and then a possible rain of enriched gas from the larger galaxy provides the fuel to sustain the firestorm. This tiny, blazing galaxy is not just a passive companion. It is an active participant in a cosmic exchange, its brilliant starburst a direct and glowing consequence of its dance with a giant. It makes you wonder how many of the tiny, glowing galaxies we see scattered throughout the cosmos are shining not solely from their own power, but because they are feeling the gravitational touch or catching the cosmic runoff of a larger, dominant neighbor. This galactic exchange is not a solitary event, but part of a much larger, invisible architecture, stretching across the immense darkness between the pinwheel and its neighboring galaxies. Astronomers have mapped a faint, tenuous bridge of hydrogen gas. This is not a solid structure, but a river of raw atomic material flowing through the void, a delicate thread connecting separate islands of stars. Its existence is the ghostly signature of a past encounter, a tidal stream of gas pulled out into intergalactic space by the relentless pull of gravity. When galaxies have a close gravitational encounter, they do not need to collide head-on to leave a mark. Their mutual attraction can stretch and distort their outermost regions, pulling long, faint tendrils of gas away from their main bodies. This intergalactic bridge is precisely that, a cosmic rope of primordial fuel stretched between the pinwheel and its companions, a permanent scar from a gravitational dance that occurred over billions of years. This fragile structure reveals a crucial fact: the Pinwheel Galaxy is not a solitary wanderer. It is the dominant member of its own small group of galaxies, a gravitationally bound family known as the M101 group. Just as our Milky Way resides in the local group with Andromeda and Triangulum, the Pinwheel is the central giant in its own celestial neighborhood. The gas bridge is the proof of their interaction, the visible evidence that these galaxies are not just passing strangers, but a connected system, constantly influencing each other's evolution through their subtle, long-range tugs. This bridge is more than just a fossil, it is a potential pipeline for the future. The gas within it is cold and neutral, the perfect fuel for forming new stars. While it is currently drifting in the emptiness between galaxies, a future close pass or merger could funnel this material back into one of the group's members, triggering a new wave of stellar birth billions of years from now. The faint river of hydrogen is a reminder that a galaxy's story is never truly isolated, but is woven into the dynamic and interconnected history of its entire local universe. But even the brilliant light of starbursts and the faint glow of hydrogen bridges cannot account for all the energy pouring from this galaxy. Peering into the pinwheel with telescopes that see in infrared light, astronomers have cataloged a different kind of mystery, point-like sources of intense heat radiation that seem to have no obvious counterpart in visible light. There are unidentified infrared sources, brilliant pinpricks of thermal energy hidden within the cosmic landscape. When you look at the same location with an optical telescope, you often find nothing but darkness, as if these powerful engines are operating behind a thick, impenetrable curtain. So what could be burning so fiercely while remaining completely invisible to our eyes? One compelling explanation is that we are finding superstar clusters in their very earliest, most violent stages of formation. Imagine a single cloud collapsing to form not one star, but 10,000 or even 100,000 stars all at once. The sheer density of newborn, massive stars within such a cluster would produce a staggering amount of ultraviolet light and heat. But if this entire cosmic nursery is still swaddled in the dense, cold cocoon of gas and dust from which it was born, the visible light is completely absorbed. Only the longer wavelengths of infrared radiation, which can pierce through the dust, escape to tell us of the inferno raging within. It is a stellar firestorm seen only by its heat signature. Another possibility is that we're seeing the aftermath of a galactic-scale collision. When two galaxies merge, vast clouds of gas can be driven together with incredible force, triggering a frenzy of star formation that is immediately shrouded in the debris of the crash. The resulting object will be a hyper-compact, dust-enshrouded starburst, a single point of intense infrared light marking the site of a cosmic pile-up. But the most intriguing possibility is that some of these sources represent something entirely new, a class of object we have not yet classified. Could they be regions where star formation is proceeding in a mode we have never witnessed, perhaps at efficiencies thought to be impossible? Or do they hide something more exotic at their core, like an intermediate mass black hole rapidly accreting material from a particularly dense and dusty disk? Each unidentified source is a question mark, a reminder that for all we have learned about the Pinwheel Galaxy, it still holds its secrets close, cloaking some of its most energetic processes in a veil of cosmic dust. What other invisible phenomena are we missing, simply because we have not yet learned to see in the right light? Even the galaxy's invisible magnetic aura tells a story of past violence. When astronomers tune their radio telescopes to the pinwheel, they detect a vast diffuse halo of radio waves enveloping the entire spiral disk. This emission does not come from stars, but from something far more ethereal, cosmic rays and magnetic fields that permeate the space between the stars. The truly strange part is its shape. This radio halo is not a perfect sphere. It is lopsided, stretched and brighter on one side of the galaxy than the other. It is as if the galaxy's invisible energy field has been smeared across the sky. This asymmetry points directly to a turbulent history. One leading explanation is a past merger. When two galaxies collide and merge, it is not just stars and gas that get thrown into chaos. Their magnetic fields become tangled and amplified, and the immense shockwaves from the collision can act like a giant particle accelerator, injecting a flood of high-energy cosmic rays directly into the galactic halo. If this merger was not a perfectly even union, but a glancing blow or an uneven assimilation, it would have dumped this energetic material more heavily on one side, creating the lopsided radio glow we see today. The halo is a permanent scar, a fossilized imprint of that ancient cosmic crash, but there is another force at work, the galaxy's own motion through space. The pinwheel is not stationary, it is sailing through the tenuous gas of the intergalactic medium. As it moves, it experiences a kind of cosmic headwind, a resistance that pushes and compresses the magnetic fields and cosmic rays on the leading side, making that part of the halo brighter and more concentrated. The trailing side, by contrast, is stretched out and fainter, like the wake behind a ship, so this distorted radio silhouette could be a combination of both an ancient, violent merger and the ongoing, gentle pressure of its journey through the void. It forces us to see the galaxy not just as a collection of stars, but as a dynamic entity with an invisible, energetic atmosphere that is still reacting to events from billions of years ago. What other hidden pressures are silently sculpting the spaces between the stars? This invisible magnetic pressure shapes the stars we can see, yet even among its brilliant population, a specific type of giant is strangely absent. The Pinwheel Galaxy appears to be suffering from a red supergiant problem. These are the final, bloated form of the most massive stars, the swollen behemoths destined to explode as core-collapse supernova. Based on our best models of stellar evolution, astronomers expected to find hundreds of these cool, immense stars glowing like crimson embers across the spiral arms. But when they look, the numbers do not add up. There is a glaring shortage of red supergiants. Where have all the giants gone? One possibility is that our models of how massive stars live and die are subtly flawed. Perhaps the stars in the pinwheel are evolving differently, skipping or rushing through the red supergiant phase faster than we thought possible. In this scenario, a star might swell into a red supergiant for only a brief cosmic moment before its core gives way, leading to a supernova explosion. We will be missing them simply because they are in that final stage for such a short time, a fleeting transition we rarely catch. A more practical explanation points to the galaxy's own dusty environment. The pinwheel's arms are filled with the raw materials for star formation, and that includes immense clouds of cosmic dust. A red supergiant, while incredibly luminous, emits most of its light in the red and infrared part of the spectrum. If one of these stars is born deep within a dense, dark cocoon of dust, that same dust could absorb its reddish light and re-radiate it as invisible infrared warmth, effectively rendering the star invisible to our optical telescopes. The giant would be there, but hidden behind a curtain of its own making. The most profound possibility, however, challenges our understanding of star formation itself. It is called the initial mass function, a fundamental rule that predicts how many stars of each size a galaxy will form. We assume that for every handful of small, common stars, a galaxy will make a few medium-sized ones and only a rare, massive giant. But what if the Pinwheel Galaxy breaks this rule? What if, for reasons we do not yet understand, it is simply not producing as many of the most massive stars as our standard model predicts? A different initial mass function would mean the galaxy's entire stellar population is skewed, resulting in fewer of the massive stars that ever become red supergiants in the first place. This missing piece of the stellar population is more than a simple counting error. If we cannot accurately account for these stars, our predictions for how many supernovae the galaxy should produce and how quickly it enriches its gas with heavy elements become uncertain. The silent absence of these crimson giants leaves a hole in our story of the galaxy's life and death cycle. This faint, widespread X-ray glow is the galaxy's fever chart. Across the entire disk of the pinwheel and extending into its halo, space itself is shimmering with an invisible light, a diffuse emission of X-rays. This is not the brilliant pinpoint of a source like ULX-1, but a soft, all-pervading radiance that tells a story of collective violence. Its source is a superheated plasma, a thin gas with a temperature of millions of degrees, a testament to the sheer amount of raw energy being pumped into the galaxy's ecosystem. How does a galaxy-wide sea of gas reach such an incredible temperature? The primary engine is the relentless combined fury of supernova explosions and the powerful stellar winds from its most massive, short-lived stars. Each supernova acts as a titanic bomb, and each stellar wind is a constant supersonic gale. Together, they heat the surrounding interstellar gas to unimaginable temperatures, creating this pervasive, high-energy fog. The distribution of this hot gas is a crucial clue. It is not uniform. It is often brightest and most extensive along the spiral arms, precisely where star formation is most frantic. This directly links the heat to the creative destruction of massive stars, but the glow does not stop at the star-filled disk. It also forms a vast, faint corona in the halo, above and below the galaxy. This tells us that the energy from these explosions is so immense it can blow gas clear out of the galactic plane, creating a hot atmosphere that envelops the entire spiral structure. This is the galaxy's energy budget laid bare. The heat from stellar deaths must go somewhere, and here we see it being distributed on a truly galactic scale, a thermal signature of the violent feedback loop that governs the galaxy's evolution. The temperature of this gas is another vital piece of the puzzle. By measuring exactly how hot it is, astronomers can calculate the total energy injected by all the supernovae over millions of years. This allows them to determine if the galaxy's star formation is driving a gentle breeze or hurricane force wind, slowly regulating its own growth by heating up and expelling the very fuel it needs to make new stars. This faint X-ray whisper is the ghost of stellar fury past, a permanent reminder that creation and destruction are two sides of the same cosmic coin. This pervasive heat is not the only sign of a galaxy shaped by external forces. Deep radio observations of the pinwheel reveal that its vast ocean of neutral hydrogen gas is not lying flat. The atomic fuel that should form a smooth disk aligned with the bright stars is instead warped, tilted like a crooked hat sitting on the galaxy's luminous head. This is not a small imperfection. It is a large-scale distortion of the galaxy's primary reservoir of star-forming material. How does an entire galactic disk become bent? One of the prime suspects is the invisible hand of dark matter. The galaxy's massive dark matter halo may not be perfectly symmetrical. If this phantom scaffold is itself slightly flattened or lopsided, its gravitational pull would tug unevenly on the gas disk, slowly twisting it out of its original alignment over billions of years. The gas, being more diffuse and responsive than the stars, is the first component to show the strain, warping under the influence of the invisible giant that cradles the entire galaxy. But dark matter is not the only gravitational sculptor. The pinwheel satellite galaxies like NGC 5474 exert their own persistent tugs. A recent close gravitational encounter with one of these companions could have been enough to torque the gas disk, setting it oscillating in a slow cosmic wobble. The stars more tightly bound by gravity would resist this twisting, leaving the looser gas to bear the brunt of the distortion. It is like jostling a bowl of water. The bowl itself, representing the stars, moves only a little, but the water inside sloshes and tilts dramatically. This warp has profound consequences for the galaxy's dynamics. A tilted gas disk creates a complex and unstable environment. As the galaxy rotates, the warped gas layers rub against each other and against the flat stellar disk. This friction can generate shock waves that compress the gas, potentially triggering the birth of new stars in unexpected places, far from the traditional spiral arms. It also changes how gas flows inward to feed the galaxy's core. The warp material may not fall in smoothly, instead arriving in clumps and streams, affecting whether a central black hole, if it exists, receives a steady diet or experiences violent, sporadic feasts. The crooked disk is far more than a curiosity. It is a live demonstration of a galaxy in a state of dynamic adjustment, its simplest components forced into a complex dance by the unseen forces that govern its existence. These brilliant stellar ghosts glow with an unexpected ferocity. Among the population of planetary nebulae in the Pinwheel Galaxy, astronomers have identified a group that shines with a startling intensity, far outshining similar objects in our own galactic neighborhood. A planetary nebula is the final, beautiful breath of a dying sun-like star, a luminous shroud of gas ejected into space as the star's core shrinks down to a white dwarf. There are typically delicate, glowing clouds, but here in M101, some of these cosmic butterflies have the brilliance of eagles. How can the last gasp of a star be so incredibly powerful? The light of a planetary nebula comes from its central white dwarf, a stellar ember hot enough to flood the surrounding ejected gas with intense ultraviolet radiation, causing it to fluoresce. The brightness of this glow depends on two key factors: the mass of the central star and the composition of the gas it illuminates. One compelling explanation is that the Pinwheel Galaxy is home to a population of progenitor stars that are simply more massive than those typically forming planetary nebulae in the Milky Way. A heavier star leaves behind a heavier and therefore hotter white dwarf. This hotter stellar cinder pumps out more ultraviolet energy, lighting up its expanding shell of gas with a fiercer, more luminous glow. It is the difference between a 100-watt bulb and a 500-watt bulb, illuminating the same lampshade. The other piece of the puzzle lies in the gas itself. The chemical makeup of the interstellar medium in the pinwheel spiral arms is different from our own, richer in elements heavier than hydrogen and helium, what astronomers call metals. When a planetary nebula forms within this pre-enriched environment, its expanding shell is already seeded with these metallic elements. Certain elements like oxygen and neon are exceptionally efficient at converting the central star's invisible ultraviolet light into the visible glow we observe. A nebula rich in these metals will naturally shine brighter than a more pristine, hydrogen-dominated one receiving the same amount of energy, so the unusual luminosity of these objects is a direct signature of the galaxy's vibrant and violent life cycle. It points to a history of furious star formation that has not only produced more massive stars, but has also chemically enriched the galactic environment, creating the perfect conditions for these spectacular final acts. The brilliant death of a single common star becomes a measuring stick for the entire galaxy's history of stellar birth and elemental creation. This invisible structure of force guides the galaxy's very breath. Woven through the pinwheel's spiral arms, astronomers have mapped a surprisingly organized and powerful magnetic field, a vast invisible skeleton that traces the galaxy's most prominent features. This is not a chaotic or random energy, but a coherent field with lines of force that run for thousands of light years, perfectly aligned along the length of the arms themselves. How does a galaxy build and maintain such an immense, orderly magnetic architecture? The engine for this cosmic dynamo is the galaxy's own rotation. The pinwheel is a spinning whirlpool of stars and gas, and this motion, combined with the churning turbulence from supernova and stellar winds, acts like a self-exciting generator. It takes weak primordial magnetic seeds and stretches, twists and amplifies them into the strong, organized field we observe today. The spiral density waves that define the galaxy's shape are crucial here. As gas flows into these waves, it is compressed, and this squeezing action also concentrates and aligns the magnetic field lines, painting them along the arms like cosmic brushstrokes. This magnetic field is far from a passive decoration. It is an active player in the galaxy's evolution. Its influence begins at the very start of a star's life. Within the giant molecular clouds that dot the arms, the magnetic field provides a form of cosmic support, a pressure that fights against the force of gravity trying to collapse the cloud. This magnetic resistance can slow down star formation, preventing a galaxy from burning through all its fuel in a single frantic burst. It acts as a regulator, ensuring stars are born at a sustainable pace. Yet when a cloud does become too heavy and collapses, the field guides the flow of gas inward, funneling material onto the growing protostar and even influencing the rotation of the resulting planetary systems. The field also serves as a highway and a trap for the galaxy's most energetic particles. Cosmic rays, which are subatomic particles accelerated to nearly the speed of light by supernova shocks, travel along these magnetic highways. The field lines channel their motion, preventing them from simply flying off into intergalactic space and instead keeping them contained within the galaxy, where their energy contributes to the heating and ionization of the interstellar medium. This intricate magnetic web is the silent framework upon which the visible galaxy is built, a force that both nurtures and constrains the cycles of birth and death. It reveals a universe where even emptiness is structured and where invisible lines of force write the rules for everything we see. This invisible magnetic architecture is itself a witness to ancient acts of destruction. Wrapping around the Pinwheel Galaxy are the faintest of stellar currents, ghostly rivers of stars that trace the final orbits of galaxies long since devoured. These are tidal streams, the luminous scars left behind when a dwarf galaxy ventures too close to the immense gravitational pull of its giant host. Spotting them is one of the most difficult tasks in modern astronomy. There are not brilliant arms or dense clusters, but an extremely faint, diffused glow, a whisper of starlight against the profound blackness of space. Detecting these streams requires painstakingly subtracting the light from billions of foreground stars within the pinwheel itself and from our own Milky Way, searching for a subtle, coherent flow in the remaining starlight. It is like trying to hear a single, soft voice in a roaring stadium. The presence of such streams is a direct testament to the pinwheel's cannibalistic past. Each one is a fossilized record of a meal, a smaller galaxy that was torn apart, its stars stripped away and scattered into long, looping arcs that now orbit silently within the vast dark matter halo. These streams tell us the pinwheel has not grown in isolation. It has actively consumed its smaller neighbors, growing in mass and size by absorbing them over billions of years. Their specific paths are a goldmine of information. The shape and direction of a stellar stream act as a cosmic speed camera, recording the precise trajectory of the devoured dwarf and mapping the gravitational field of the host galaxy in extraordinary detail. By studying the curve of these stellar rivers, astronomers can weigh the pinwheel's dark matter halo and even probe its shape, determining whether it is a perfect sphere or a flattened spheroid. Yet the absence of obvious large streams is equally telling. If the pinwheel has been a particularly voracious eater, having consumed many small galaxies in rapid succession, the evidence might be thoroughly mixed. The individual streams would overlap and blend together, their distinct signatures churned into a smooth, faint fog of stars in the galaxy's outer halo, a homogenized background of ancient conquests. So the search for these stellar ghosts is more than a hunt for cosmic archaeology. It is a direct investigation into the predatory nature of galaxy growth, revealing a history written not in brilliant starlight, but in the faint, fading echoes of galaxies that are no more. The chemical map of the Pinwheel Galaxy tells a story of a turbulent and fragmented past. In most large spiral galaxies, there is a predictable pattern, a smooth metallicity gradient where the concentration of heavy elements steadily declines from the rich, crowded core out to the sparse galactic fringe. The center, having witnessed countless generations of stars living and dying in rapid succession, is a polluted metropolis of cosmic metals. The outer regions, by contrast, are the pristine countryside, composed of gas that has seen little stellar activity. Yet when astronomers chart this chemical landscape across M101, they find the gradient is not smooth at all. It is broken, patchy, and full of surprises. In some regions of the outer disk, the metallicity is unexpectedly high, as if a pocket of the inner city had been suddenly transplanted to the rural outskirts. In other parts closer to the center, the metal levels can dip strangely low. This is not the orderly chemical evolution we expect from a galaxy that formed calmly from the inside out. This jagged metallicity profile is the signature of a violent and chaotic assembly. It points to a history where large chunks of the galaxy were built from separate clouds of gas, each with its own distinct chemical history, that only later merged together. Imagine trying to create a smooth, layered cake by violently mashing together several smaller cakes that were each baked with different recipes and ingredients. The final product would be a messy, inconsistent blend, and that is precisely what we see in the pinwheel stars. These chemical anomalies are permanent fossils. A clump of stars in one spiral arm with unusually high metallicity could be the remnant of a devoured dwarf galaxy that itself had a vigorous period of star formation before being cannibalized. Conversely, a region of low metallicity might be a pocket of primordial, unenriched gas that was dragged in from the intergalactic void during a late-stage accretion event, a fresh ingredient added to the mix long after the main galaxy had formed. This chaotic chemical distribution has a direct impact on the types of stars that can form. Planets, particularly rocky worlds like Earth, are built from these heavy elements. A stellar nursery born in a metal-rich pocket of an outer arm would have a much higher abundance of the raw materials needed to form terrestrial planets than a similar nursery in a metal-poor region. The very potential for planetary systems and perhaps even life may be unevenly sprinkled across the pinwheel's expanse, dictated by the random chemical scars of its violent birth. What does it mean for a galaxy story when its fundamental building blocks are so clearly stitched together from disparate and conflicting histories? A sudden, brilliant crackle of radio noise once seemed to echo from the pinwheel's direction. For a fleeting moment, it had all the hallmarks of a cosmic mystery known as a fast radio burst, an enigmatic blast of radio waves that can release more energy in 1,000th of a second than our sun does in 3 days. These signals are the universe's most powerful and puzzling radio flashes, often originating from billions of light years away. The detection from the vicinity of M101 created a surge of excitement, a hope that we might have caught one of these cosmic lightning strikes from a known, relatively nearby galaxy. It would have been a perfect laboratory to study a profound enigma, but the universe is a master of cosmic misdirection. Follow-up observations with multiple telescopes peering across different wavelengths of light almost always revealed a far more local culprit. The culprit was not a cataclysm in the Pinwheel Galaxy, but a flaring star right here in our own Milky Way, a magnet or a particularly active stellar remnant that just happened to lie along the same line of sight. It was like hearing a loud bang and thinking it came from a distant mountain, only to realize it was a car backfiring just down your own street. This process of elimination is a fundamental part of the scientific hunt. Every false alarm is not a failure, but a refinement of our methods. It forces astronomers to be meticulous, to confirm and reconfirm, ensuring that when a true extragalactic fast radio burst is finally pinned to a galaxy like M101, the discovery will be unshakable. The search continues because the potential reward is so immense. Finding one of these bursts originating from within the pinwheel would be a monumental event. It would give us a known distance, a known galactic environment, and a chance to finally understand what kind of cosmic engine can produce such a short, unimaginably powerful signal. Is it the final death cry of a collapsing star, the violent merger of two ultra-dense neutron stars, or something even more exotic that we have not yet dreamed of? The Pinwheel Galaxy, with its history of stellar violence and strange phenomena, remains a prime candidate for hiding such a secret. Its spiral arms, filled with the ghosts of supernova and the fury of stellar birth, could very well be the stage for the next great cosmic flash, a momentary radio scream that could rewrite our understanding of the universe's most energetic events. The Pinwheel Galaxy burns with the light of dying giants, Among its countless stars, astronomers have identified a surprisingly large population of a rare and violent breed, Wolf-Rayet stars. These are not ordinary suns. They are the exposed, superheated cores of the most massive stars in the universe, stars that have literally blown away their own outer layers. Imagine a star so powerful that it rips off its own skin, casting it into space in a ferocious, continuous gale. This is the final, frantic stage for stars born with more than 20 times the mass of our Sun, a brief and brilliant prelude to a supernova. These stars are cosmic pressure cookers operating at the absolute limit. Their surfaces rage at temperatures exceeding 50,000 degrees Celsius, and they drive stellar winds of unimaginable force. These are not the gentle solar breezes our Sun emits, but supersonic hurricanes of charged particles blasting outward at millions of kilometers per hour. This incredible outflow strips the star down to its core, peeling back the layers to reveal the elemental forge within. The winds are so dense and powerful that they literally cocoon the star in a shroud of its own expelled material, a glowing envelope of gas that creates the unique and brilliant spectrum astronomers use to identify them. This violent process is a crucial act of cosmic recycling. As a Wolf-Rayet star sheds its mass, it does not just throw off simple hydrogen and helium. It ejects vast quantities of heavier elements freshly synthesized in its nuclear furnace, including life-giving carbon and life-sustaining oxygen, as well as iron and neon. These elements are blasted into the surrounding interstellar medium, seeding the galactic environment with the raw materials for future planets and, potentially, life. Each of these stars is a frantic factory, polluting its neighborhood with the very elements that make rocky worlds like Earth possible. Their existence is fleeting, a mere blink in cosmic time lasting only a few 100,000 years. A Wolf-Rayet star is a ticking time bomb, its core fusing elements at a breakneck pace as it races toward its own inevitable destruction. The sheer number of these stars within the pinwheel's arms tells us this galaxy is currently a hotbed for the formation of stellar behemoths. It suggests a recent, widespread episode of intense star formation that produced a generation of stars destined for spectacular deaths. The presence of so many Wolf-Rayet stars essentially guarantees a future filled with gamma-ray bursts and superluminous supernova, the most energetic explosion since the Big Bang. They are the smoking gun, the final warning shot before the galaxy's next great stellar cataclysm. What would it be like to witness the final moments of a star that has already spent its life in such a state of glorious, self-destructive fury? These dying Wolf-Rayet stars are not the only volatile giants in the galaxy. Lurking within the pinwheel's spiral arms are stars so unstable they exist on the very edge of self-destruction, known as luminous blue variables. These are not merely massive stars, they are the true titans of the stellar world, cosmic behemoths so large and luminous that they can barely hold themselves together. A luminous blue variable is a star in a state of perpetual identity crisis, spending its life in a violent tug of war between radiation and gravity. The intense outward pressure from its own nuclear fusion battles against the crushing weight of its immense mass, a balance so delicate it leads to sporadic, colossal eruptions. In these outbursts, the star does not just shed a gentle stellar wind, it violently ejects entire shells of its own surface, throwing off a mass equivalent to our entire Sun in a single event. It is a star literally tearing itself apart, while a confirmed luminous blue variable in M101 remains elusive. The galaxy's intense star-forming regions are prime hunting grounds for these rare objects. Astronomers actively search for stars that exhibit the telltale signs, dramatic and unpredictable variations in brightness coupled with spectral revealing dense, slowly expanding shells of ejected gas. Finding one would be like discovering a cosmic time bomb with a flickering fuse. Studying these stars is crucial because they represent a fleeting, volatile phase in the life of the most massive stars ever born, those tipping the scales at over 50 solar masses. A luminous blue variable is thought to be a direct precursor to a Wolf-Rayet star, the final frantic stage before the star finally blows away its outer layers to reveal its searing core. Some scientists even theorize that the most extreme supernova explosions, the hypernova thought to produce long-duration gamma-ray bursts, are the final acts of these unstable blue giants. Understanding a luminous blue variable is like studying the final, violent tremors before a monumental earthquake. Their giant eruptions are a dominant mechanism for enriching the galaxy, seeding the interstellar medium with enormous amounts of processed material, including nitrogen and other elements crucial for life. Each eruption permanently alters the star's own evolution, peeling back its layers and determining its ultimate fate. The quest to find one in the Pinwheel Galaxy is a search for a missing link in the life cycle of stellar titans, a chance to witness a star in its most unstable and dramatic state, offering a front-row seat to the forces that shape the chemical and energetic future of an entire galaxy. What would it mean to finally catch one of these celestial giants in the act of one of its self-destructive fits? This vibrant, blue-tinted glow defines the entire character of the Pinwheel Galaxy. From our distant vantage point, M101 does not look like a stately, mature spiral. It looks like a galaxy in its prime, blazing with the light of its brilliant, short-lived blue stars and swollen with the pink glow of stellar nurseries. This overall youthful appearance is the cumulative effect of all its strange phenomena, a galaxy-wide personality shaped by its chaotic history. Why has this particular spiral maintained such a frantic pace of creation, while others of its kind have settled into a more sedate middle age? The answer lies in its dynamic isolation and its rich reserves of fuel. Unlike our Milky Way, which resides in a more crowded galactic neighborhood, the Pinwheel is the dominant giant in a relatively small group. This means it has largely avoided the violent, gas-stripping collisions that can quench star formation in denser galaxy clusters. Instead, its encounters have been with smaller satellites, interactions that stir and compress its vast gas reservoirs without completely destroying them. Each close pass, like the ongoing dance with NGC 5474, acts as a trigger, shaking the galactic gas and igniting another wave of star birth. Furthermore, its enormous, clumpy halo of neutral hydrogen represents a deep well of potential, a fuel tank that is still far from empty. This constant, gentle stirring, combined with an abundance of raw material, has kept the Pinwheel in a sustained state of creative frenzy. But this vibrant youth cannot last forever. The very process of star formation is self-limiting. All those brilliant, massive stars living fast and dying young are pumping immense energy back into the galaxy through supernova and fierce stellar winds. Over billions of years, these galactic winds will gradually blow away the remaining cool gas, or heat it to such high temperatures that it can no longer collapse to form new stars. The galaxy's future likely holds a gradual quieting. The frantic blue light of massive stars will fade, leaving behind the longer-lasting, yellower glow of smaller, older stars. The spiral arms, once sharp and defined by glowing nebulae, may become fainter and more dusty. However, the story may not end with a simple fade to black. A future merger with a sizable companion galaxy, or even the eventual inflow of gas from the intergalactic bridge it is connected to, could deliver a fresh infusion of fuel. This could spark one last glorious burst of star formation, a final firestorm before the galaxy truly settles into a quiet old age. The Pinwheel's current brilliance is a snapshot in a billion-year story, a vibrant chapter in a life that is still being violently, beautifully written. The galaxy breathes as a single living entity, where every violent event is a link in an unbroken chain of cause and effect. The gravitational tug of its satellite galaxies stirs the vast, clumpy sea of hydrogen gas, compressing it into the dense clouds that collapse into stellar nurseries like NGC 5462. This frantic star birth populates the spiral arms with massive, short-lived stars that burn brilliantly and die young, exploding as supernova. These stellar cataclysms do more than just light up the cosmos. They pump immense energy back into the system, heating gas to millions of degrees and driving the galactic winds that blow material clear out of the disk. This very same fury forges the heavy elements that seed the surrounding gas, enriching it for the next generation of stars and planets. This cycle of creation and destruction directly powers the galaxy's most bizarre phenomena. The torrent of material from a supernova or a stellar companion can funnel onto a black hole, pushing it into a super Eddington state and creating an ultraluminous X-ray source like ULX-1. The chemical legacy of these explosions is written in the intense glow of the galaxy's brilliant planetary nebulae and the unique spectra of its Wolf-Rayet stars. Even the galaxy's missing red supergiants and anomalous Cephate variables are clues to this relentless cycle, their strange behavior shaped by the dusty, metal-rich environment that the supernova themselves help to create. The faint tidal streams of devoured dwarf galaxies and the warped hydrogen disk are not separate stories. They are the ancient triggers that set this entire process in motion, providing the initial gravitational nudges that began the star-forming cascade. The pervasive X-ray glow and the lopsided radio halo are the thermal and magnetic signatures of this ecosystem in motion, the visible symptoms of the energy flowing through the galaxy structure. From the faintest tidal bridge to the most brilliant stellar explosion, every phenomenon is a thread in a single, dynamic tapestry. The Pinwheel Galaxy is not merely a collection of stars. It is a grand self-regulating engine where gravity, radiation, and matter are locked in a continuous dance, a cosmic ecosystem where every death feeds a new birth, and every mystery solved reveals a deeper, more beautiful connection. This grand cosmic engine, from its silent core to its flaring arms, reveals a single profound truth. The 28 strange phenomena of the Pinwheel Galaxy are not isolated riddles, but interconnected threads in a single dynamic tapestry. We have journeyed past a star that broke a fundamental limit, peered into a core missing its dark heart, and witnessed a beacon of X-ray light defying every rule of brightness. We have seen how its lopsided spiral arms, brilliant star factories, and phantom dark matter scaffold all work in concert, a self-regulating system where gravity's pull and stellar fury exist in an endless creative dance. This galaxy is more than a beautiful spiral. It is a living laboratory where the universe conducts its most extreme experiments. It teaches us that our cosmic rulebook is always a draft, forever being revised by the next observation, the next anomaly. The true wonder is not that we have solved these mysteries, but that such a familiar patch of sky still holds so many. For every question we answer, the Pinwheel Galaxy poses 10 more, reminding us that the universe is vast, strange, and humblingly beautiful. So tell us, which of its secrets captured your imagination the most? Was it the missing black hole, the impossible supernova, or the brilliant, hidden fire of ULX-1? Let us know in the comments below and subscribe to continue unraveling the universe's greatest puzzles with us. The cosmos is full of wonders, and our journey has only just